let's take a closer look at the qualitative ideas behind inverse mappings. This will lead to the notion of cardinality. Now, recall, we have a mapping F carrying the set X to the set Y. We'll call F a one-to-one correspondence or bijection if and only if F is one-to-one and onto. If that's the case, then there exists an inverse mapping to F. We call it F inverse, and we denote it F with superscript -1. F inverse carries Y back to X with the conditions. F inverse composed with F is the identity mapping on X. F composed with F inverse is the identity mapping on Y. So whatever F does to X, we can undo with F inverse. Whatever F inverse does to Y, we can undo with F. Note, F inverse is also a one-to-one correspondence. Now, the idea underlying all of this, if I can construct a one-to-one correspondence between X and Y, then as far as sets are concerned, X and Y are the same set. So what's happening is we're taking all the points in X. When we apply F, we just relabel them points with Y labels. So we have the same set, just with different labels. As an example, let's consider X equal to the set 1, 2, 3. Y is the set ABC. I have a one-to-one correspondence between X and Y by sending 1 to A, 2 to B, 3 to C. So here we have the set X being relabeled as ABC, so with the Y labels. So here these are essentially the same set. What makes them the same is the quality of having 3 elements. Now, we want to make that precise. So, since we're talking about equality of sets, we should have an equivalence relation. Now, if I want to put an equivalence relation on all the sets that we're interested in, okay, recall we don't have a set of all sets. Instead, we work with the class of all sets. We won't be precise about what that is, but it'll include everything we work with, like the natural numbers, the integers, the rationals, the reals, and so on. Now, if X and Y are 2 sets, we'll say that X is related to Y if and only if there exists a one-to-one correspondence carries X to Y, called F. To show that we have an equivalence relation, we need to show that our relation is reflexive, symmetric, and transitive. So recall, for reflexive, I want to show that X is related to X. I could do that by just using the one-to-one correspondence given by the identity map on X. For symmetric, I want to show if X is related to Y, then Y is related to X. So if X is related to Y, then we have some one-to-one correspondence F carrying X to Y. We noted there exists an F inverse carrying Y to X, which is also a one-to-one correspondence. So we have symmetric. Then for transitive, okay, if we have X related to Y, Y related to Z, we're going to show that X is related to Z. So we'll have one-to-one correspondences F and G. So F will carry X to Y, G carries Y to Z. If we take the composition, G composed with F, we've seen last time, composition of one-to-one correspondences gives another one-to-one correspondence. So this mapping here, carrying X to Z, gives a one-to-one correspondence between X and Z. So transitive. Since we have an equivalence relation, we can consider its equivalence classes. We fix a set X, then its class is just going to be all sets Y, such that X and Y can be put in one-to-one correspondence with each other. For notation, we'll denote the class as our set X in bars. We call that the cardinality of X. So the cardinality is going to be an equivalence class. Now, we would say that X and Y have the same cardinality if and only if there exists a one-to-one correspondence F carrying X to Y. We're interested in 3 types of cardinalities. First, we have those for finite sets. In that case, the cardinality is just the number of elements in the set. We have countably infinite sets. These are the sets which can be put in one-to-one correspondence with the natural numbers. Then everything else we call uncountably infinite. For here, we're only going to consider cardinality of finite sets. And then we save the last two for the next talk. Before we could talk about cardinality of finite sets, okay, we need to review the natural numbers. If we were to do a rigorous overview of the natural numbers, we'd bring out all the piano axioms and explain those. For here, we're just interested in the basics. Now, recall, for the natural numbers, okay, depending on what book you're reading, you either have 0 or 1 as the first element. To construct these, I could start with the empty set and then just keep taking successive power sets. We've seen from that how to get all finite binary sequences, and those we can consider our natural numbers. Okay, to make it more familiar, convert from binary to base 10. Once we have the set, we can well order the set. So first we'll have the total ordering given by taking less than or equals. For the well ordering, that's going to mean there's going to be a first element, so it'll be 1 or 0. Then every natural number is going to have a successor relative to less than or equals. So if we take the number n, its successor is going to be n plus 1. With respect to our total ordering, every element is going to have a unique predecessor except for our first element. Now, what this gets us, for instance, is a way to do addition. So if I want to add m plus n, I would take n and then take the successor m times. One last item we use in doing proofs with the natural numbers is the well ordering principle. So this says every non-empty subset of the natural numbers has a smallest element. We have the usual picture of the natural numbers. So we start at 1, we repeatedly apply the successor function. Okay, this goes off to infinity. For an example of addition, okay, we take 2 plus 3. So we'll take 2 and apply the successor function 3 times. So 2 goes to 3, 3 goes to 4, 4 goes to 5. 2 plus 3 is equal to 5. That works in the other order. If we take our picture, stand it vertically, then the arrows should suggest climbing a ladder. That leads to our principle of mathematical induction. Now, we have enough, so we can go back to cardinality. So the definition, a non-empty set X is called finite if and only if there exists a one-to-one correspondence F that carries set 1 through n to X. So here, we're going to take X. I'm going to start labeling its elements with the natural numbers. So we start with 1, and then we go in order. If we run out of elements to label, then we say that our set is finite. So for example, okay, I'll take 1, 2, 3, 4, 5. Number of fingers on this hand is finite. I'd like to say that I have 5 fingers, but the statement that X has n elements is not well defined yet. So what I would need to show is that we have X a finite set. We only have one set of the form 1 through n in its equivalence class. So that's the same as saying if we have the set 1 through n, the set 1 through m, we take the cardinalities and they're equal, then we have to have the m is equal to n. Then I could say that X has n elements. Now, for that I need the following lemma. So I'll assume that X is a non-empty set with at least 2 elements. We'll pick an X0 and X. And our statement is there exists a one-to-one correspondence F carrying 1 through n to the set X, if and only if there exists a one-to-one correspondence F prime carrying 1 through n minus 1 to X, and then we throw away X0. So when we have finite sets, we can build or take apart one-to-one correspondences one element at a time. Now, for the proof, okay, if we go to the left, well, there's not a lot of work here. We already have f prime. I want to put x0 back into the function, okay, as a value. So I'll just stick it in at the end. So we'll define f to be equal to f prime for any j from 1n minus 1. And at the end, we have f of n equal to x0. And I'll leave it to you to show it's a one-to-one correspondence. In the other direction, okay, so the idea here is, okay, we can list things like this in this picture. if x0 is at the last element, then we could just chop it off. Okay, we just restrict our domain to 1 to n minus 1. Then that'll remove x0 from our values. Now, if x0 is not the last element, we'll just remove it anyway, and that can move the last element to the spot where x0 was. So formally, okay, since f is onto, so f of I is equal to x0, we'll call f of n x1, I'm going to define f prime in the following way. So if we're in the set of all j from 1 to n, but not equal to I or n, we'll just define f prime equal to f. Otherwise, I'll define f of I equal to x1. Okay, so that's just filling the hole in, and I'll leave it to you to show that's a one-to-one correspondence. So that's our lemma. Let's apply our lemma to show that the number of elements in a finite set is well defined. So theorem. If the cardinality of 1 through m is equal to the cardinality of 1 through n, then we must have m is equal to n, then that's the number of elements in each of these sets. For the proof, we assume there exists a one-to-one correspondence f carrying 1 through m to 1 through n. Let's recall what m is. So if I start at 1 and apply the successor function m minus 1 times, I get to m. In the other direction, if I start at m, apply the predecessor function m minus 1 times, I get to 1. Likewise for n. Now, if these sets have more than 2 elements in them, okay, by our lemma, there exists a one-to-one correspondence f1 that carries 1 through m minus 1 to 1 through n minus 1. We repeat this process using this idea about predecessors. Eventually this process is going to terminate, taking off one at a time. It'll stop when we get down to 1 element in one of these sets, but because we have a one-to-one correspondence, that means both sides will have to have 1 element. Now, that'll give us the following equations. Either m minus n plus 1 is 1, or n minus n plus 1 is 1. In either case, we get m is equal to n, and we have our theorem. Now, using that, we have the following corollary. So every non-empty subset B of the set 1 through n is finite. If B is proper, then the cardinality of B, okay, the number of elements in B, is between 1 and n, including 1. For the proof, we use induction on n. So for the base case, when n is equal to 1, there's nothing to show. For the induction step, okay, we suppose it's true when n is equal to k. We want to show the corollary is true when n equals k plus 1. So we'll let B be a non-empty subset of 1 through k plus 1. If it's not everything, then 2 things can happen. Either B is equal to 1 through k, or B, throw away k plus 1, is a proper subset of 1 through k. If it's the first case, then there's nothing to show. Otherwise, okay, by the induction hypothesis, we have that B minus k plus 1 is finite, and the number of elements of B minus k plus 1 is between 1 and k, including 1. Now, if we apply the lemma, that's going to let us add in the k plus 1. So that B is finite, and the number of elements in B is between 1 and k plus 1, including the 1. And that's our result. To state the corollary in general, A is a finite set with n elements. B is a proper subset of A. Then there exists no one-to-one correspondence between B and A. Also, there exists a one-to-one correspondence F carrying B to the set 1 through m, where m is strictly less than n. Now, worth stating on its own, A is finite. Then there's no one-to-one correspondence of A with a proper subset of A. So to use this to test for infinite sets. For example, to see that the natural numbers are not finite, okay, I consider the mat f of n equal to n plus 1. They'll carry the natural numbers to the subset of natural numbers greater than or equal to 2. So that's a proper subset, and the natural numbers are not finite, so infinite. Now, for our next theorem, okay, this is going to let us test for cardinality without actually constructing 1-to-1 correspondences. So it could work with either onto maps or 1-to-1 maps. So if B is non-empty, okay, n is a positive integer, the following are equivalent. First, there exists an onto mapping F that carries 1 through n to B. Next, there exists a 1-to-1 G carrying B to the set 1 through n. 3, B is finite and has less than or equal to n elements. Now, for a proof, we show 2 implies 3, 3 implies 1, and 1 implies 2. We'll have the implications in any direction between our 3 statements. So they'll all be equivalent. Now, for 2 implies 3, okay, we have a 1-1 map from B into 1 through n. I can identify B with its image, so G of B. Okay, and this identification is going to be a 1-1 correspondence. So that means I can identify B with a subset of 1 through n. So B is finite, and the number of elements in B is between 1 and n by our corollary. For 3 implies 1, okay, we're assuming that B is finite, and the number of elements in B is between 1 and n. I want to show that we can construct an onto map from 1 through n onto B. Now, because B is finite, there exists a 1-to-1 correspondence, G, carries 1 through m to B. Okay, and m is between 1 and n. If m is equal to n, then we're done. Otherwise, okay, if m is strictly less than n, we can define a piece of nm. It's going to carry 1 through n to 1 through m, defined as, okay, we set I to I, if I is between 1 and m otherwise. Then the map F, given as the composition of G with piece of nm, is going to be the onto map from 1 through n to B that we're looking for. Finally, for 1 implies 2, okay, we're assuming that we have our onto map from 1 through n to B. We're going to show that I can construct a 1-1 map from B into 1 through n. Now, because we have an onto map for each B and B, I can find an I in 1 through n such that f of I is equal to B. So we're just going to choose one I that goes with each B, put them together, and we'll call that set I. Now, on I, we're going to have a map to B that's going to be 1-to-1 and onto. So we'll have an inverse map when we restrict to I. So I'll call the inverse G. Then we'll have a map from B to I, which is a subset of 1 through n. Okay, this is going to be a 1-1 correspondence. So what we have here is our 1-to-1 map into the set 1 through n. So that gives our theorem. Now, the upshot of our 2 theorems is that we can count as usual. So the first theorem says all counting rules that we have apply. Second theorem says all of our overcounting rules apply. I'll explain that when we get to its example. Now, for an example of 1, we have the matching rule. So if m shirts, n pairs of pants, then we have m times n outfits. More formally, if we have a collection of finite sets, A sub I, okay, we'll say that the number of elements in A sub I is n sub I. If we take the finite Cartesian product, A sub 1 through A sub k, call that x, then that set is finite, and the number of elements in x is the product of n1 through nk. Another example of 1, if we have A and B, finite subsets of another set x, then we have the rule for union and intersection. So the number of elements in A union B is the number of elements in A plus the number of elements in B minus the number of elements in the intersection. So to see this, if I draw a Venn diagram, if I take all the elements in A, all the elements in B, put them together, when we count, we're going to double count the intersection. So if I want the precise count of the union, I have to throw away, okay, the number of elements in the intersection once. For overcounting, we could have settled for an inequality in the last example. So if A and B are finite subsets of some set X, the number of elements in A union B is less than or equal to the number of elements in A plus the number of elements in B. So to see this, It's not too tough to set up a one-to-one map from A union B to the set 1 through number of elements in A plus the number of elements in B. By our second theorem, this will give us this inequality here. Now, if we extend one union at a time, we get that a finite union of finite subsets is finite, and we have the following inequality. As a final note, we have the pigeonhole principle. Now, this isn't very involved, but it's very useful. So if we have natural numbers, m and n, with m strictly less than n, if I have m holes and n pigeons, then some hole is going to get greater than one number of pigeons. Now, to show this, we'll use proof by contradiction. So let's suppose not. So let's suppose every hole gets either 0 or 1 pigeon. That means I can set up a one-to-one map, f, going from 1 through n to 1 through m. So that's going to mean that n is less than or equal to m, which is a contradiction to our assumption. So the pigeonhole principle holds.